Good afternoon, everyone. Just give me a thumbs up if you can hear my voice. Mkosi and Varushka. Either of you can hear my voice, just give me a thumbs up, please. Okay, thank you. Thank you very much. Okay. Let's see here. Okay, let's see now. Yep. Slightly larger. Okay, it's 12. We're gonna start now. Okay, so first of all, my name is Lucian and I will be your tutor for today. Okay, those of you who have joined at the moment, do you have any questions? Anything that you're struggling with currently in physics? If you do, you can just ask me right now. If not, I will start doing some problems only if you don't have any questions for me. Okay, seems like there will be no questions. Now, today or for the past week or so, you've done motion in one dimension or motion in a plane. Okay. So we'll be covering some problems on motion in one direction and motion in a plane. Let me just see. Question 6. Let's just start. Okay, so question number 6. Now, for those of you who joined when Arnold was presenting on Monday, I think, he ended at question number 5, which is also part of motion in one direction and motion in a plane. So we are doing motion in one and two dimensions, sorry. Now, let's say question number 6, a projectile, doesn't care, we don't care what it is, some projectile, let's say it's a rock, is fired, or in this case a bullet or a cannon would be more appropriate, a cannonball, is fired in such a way that its horizontal range, let's say it's a cannon, okay? Let's say there is a cannon that's fired with a cannonball moving out of it, and it travels through the air initially moving out due to the force impacted by the cannon and then eventually being dragged back down by gravity. Now let's say that's the range, it's how far the ball travels before in the horizontal direction. So that would be the range. And then also they tell us this projectile is fired in such a way that its horizontal range is equal to 3 times its maximum height. Let's check. And this here, right at its turning point, would be its maximum height. Okay? Let me highlight that in red. This would be its height. H, the maximum height. And they tell us that a projectile is fired in such a way that its horizontal range, meaning R, is equal to 3 times the maximum height. So R is equal to 3 times the height. Okay. What is the angle of projection? Meaning, what is this angle here? Theta. Okay. At what angle should this projectile be fired? At what angle should this projectile be fired so that the range where it lands is 3 times its height? Let's go work that out. So at what angle should a projectile be fired such that its range, meaning its horizontal distance or the distance it travels horizontally, is equal to 3 times its maximum height? So the range here that I wrote down at the bottom, the range horizontally is equal to 3 times its height. So at what angle should it be fired so that that may be true? Right, let's go see. Right. Now we know that we can calculate height in projectile motion. We can calculate the height as follows. Height in projectile motion is equal to the initial velocity squared. Let me just see if you guys can see. Okay. So it's the initial velocity squared multiplied by the sine of the angle squared as well. You divide that, by the way, this is the initial velocity. You divide that, that's the initial angle that is fired at, by 2 times the gravitational constant. Okay, that is the height. Now we've already established that the height must be 3 times the height is equal to the range. Okay, we know that 3 times the height is equal to the range in this case. Okay, we want to work out what exact angle should be used so that 3 times the height, the maximum height, is equal to the range. If at any point you have any questions, just raise your hand or ask me. We also know that the formula for the horizontal range, meaning how far it goes horizontally, is equal to the initial velocity again squared multiplied by the sine of 2 times the initial angle. Note this formula. Here we have the sine for the height, we have the sine squared of the angle. Here we have the sine of 2 times the angle, the initial angle. And this one is divided by 1g, whereas the height was divided by 2g. Right? And we know from what we've been given that the maximum height is equal to 3 times the range, meaning the horizontal distance that this ball or projectile, in our case, we took it as a cannon ball. Okay, so we've been given that 3 times the height should be equal to the range. Now we've already have a formula for the height and we have a formula for the range. To remind you again, the formula for height is V initial squared, don't forget to square, times the sine of the initial angle, and that is also squared, divided by 2g, and that should be equal to the range. Now remember, it should be 3 times the height. Okay, this is the formula for the height, and it should be 3 times the height. Now the range is equal to the initial velocity times the initial angle, the sine of double the initial angle. Let me just write that neatly. Sine of 2 theta over g. Now g's will cancel out. The initial velocity, also this is initial velocity squared as well. They will cancel out as well. Initial velocity will cancel out. We will be left with on this side 3 times the sine of theta squared over 2, and on this side we're left with sine 2 theta. You don't have to write it over anything because that's cancelled. We can just write it over 1, no problem. Now we can rewrite this, okay, with all the signs on one side and all the numbers on the other. So this will be 3 over 2 left here. If we cross multiply, we'll have sine squared theta as the denominator, and in this case sine 2 theta on top. Okay, so this is where we are right now. Okay, we've managed to get up to this point using simply what we've been given and the formulas for range and height. Okay, now if I were to just clear that, let's continue. I just wrote there that it should be 3 over 2 equals to sine 2 theta over sine squared of theta. So this is the theta that we want. We want theta. We want that initial angle. We want to know at what angle should this cannonball be fired at so that the range, meaning the horizontal distance it travels, is equal to 3 times its maximum height. Now let's flip these two up over, okay? This will be 2 over 3, and in this case, it will be sine squared theta over sine 2 theta. We just flipped both of these fractions over. And there's a reason why I did that. You don't have to do that. You can just work as is. I just flipped it over. Now, using I'm going to show you now. Sine squared theta is just sine theta multiplied by sine theta. Okay? In this case, it's still 2 over 3. Now, sine 2 theta. There are two, it's an identity. Sine 2 theta is an identity. And there are 3 different ways of writing out this identity from high school math. But the easiest one, or the one you can work with now, is that sine 2 theta is equal to 2 sine theta multiplied by cosine theta. Sine 2 theta, this formula here is exactly the same as this one here. They are the same formula. Okay, it's an identity, it's a trigonometric identity, okay, from high school. You should remember that. Now here we can have one of these signs cross out, and on that side we are then left with sine, this 1/2, and then sine over cosine is tangent of theta, and on this side we're left with 2 over 3. Okay, so a half tangent is equal to 2 over 3. If we take the 2 over to that side, it's 4 thirds tangent of theta. 4 thirds is equal to the tangent of theta. So we know that the tangent of the angle that we want, theta, is equal to 4 thirds. Now this now is a more doable equation, okay? And we've done nothing new. We've just done some basic algebra, okay? 4 over 3, and we have that theta is equal to 53, and you can do this by yourself, or I can show you how to do it. You just put in your calculator the inverse tan of 4 over 3 is equal to 53.1 degrees. Okay, it's 53.1 degrees. That's the angle at which you should fire the cannonball or whatever projectile in order that the range horizontally would be equal to 3 times the height. Now you may get similar problems again in the future, so make sure you know how to do this problem or these type of problems based simply on symbols. And that is what the answer should be there, 53.1 degrees. Now, if are there any questions? By show of thumbs up or raised hands, who understood or can do this problem? If you were given this problem again, would be able to do it by themselves? Okay. Okay. If you were given this problem, who amongst you would be able to do it again? Okay, I've got Varushka Bueta saying she would definitely be able to do it again. Or if you have a question, you can ask a question. Thank you for those who've raised your hands or given a thumbs up. Parushka, if you have a question, I might be interpreting that the wrong way. If you have a question, you can just ask. Otherwise, I assume that you understood the problem and would be able to do it by yourself if you were to see it again in the future. Okay. Right in the chat. Okay, thank you. Everyone else, I assume, understood. Let's see. Let's do another problem. We'll just be doing 5 simple problems. Okay, problems that you are supposed to know when you get to your exam or semester test, which is around the corner. I assume it's March already, so your first one should be coming at the end of March. Now, let's say question number 7. We have an athlete. Okay, now this is uniform circular motion, a uniform circular motion problem. Okay, can I just ask from you guys, have you done uniform circular motion yet in class? Have you started with it? Uniform circular motion. Uh, okay, Alizwa, I assume you gave a thumbs up that you've actually started uniform circular motion. Okay, so I'm going to do one problem on uniform circular motion as it's a motion in a plane. It's uniform circular motion, but it's still two-dimensional motion. Okay, let's do this problem. They tell us that an athlete rotates a 1 kilogram discus. Okay, so we have an athlete rotating a 1 kilogram discus along a circular path. So there's a circular path. Let me just try to draw. I always try to draw what is happening because it makes it easier for me to understand. So let's say this is a discus. We have a discus here. It's terrible drawing of a discus, but let's just pretend it's a discus. And this athlete is rotating this discus in this circular path. Let's also pretend this is a circle, not some squashed circle. Now, if we were to model this discus as a particle in uniform circular motion, okay, we would be able to solve this problem. Now, let's go to what is the problem actually that we want to solve. Now, an athlete rotates this 1 kilogram. So the weight of this discus M is 1 kilogram. Okay. And the radius of the circular path, so the distance from the center of the circle to the center of the discus, is equal to R. That radius is equal to 1,06 meters. Now the maximum speed of the discus is 20 meters per second. So V equals 20 meters per second. They want you to determine the magnitude of the maximum radial acceleration of the discus. Okay, so we have the maximum speed, so we can actually determine the maximum radial acceleration. Let's go ahead and do that. Now, how do we determine acceleration in uniform circular motion? We know that the acceleration is equal to the speed squared over the radius. That is the formula that you should all know for uniform circular motion. Now, the maximum speed they've given us is 20 meters per second, and we should square that, never forget to square, divided by the radius 1,06, and that will give us a radial acceleration for this discus as, if you were to square 20 meters per second, it would give you 400 meters per second divided by 1,06. That's approximately 377 meters per second squared. This is also meters. One of the meters cancels out, leaving your answer with the units of meters per second squared, which is also the units of acceleration. And that is how you do that problem. Quite simple, actually. Everyone understand that problem? By show of hands, you understand it? It's a simple problem. It's just uniform. That's about as difficult as those type of problems can get. Okay, that's about as difficult as uniform circular motion problems can get. It's a standard type of problem. You won't see any trickery there. But now let's get to this next question. This one is interesting. Okay, there is the next three questions. It's quick, but you need to keep it follows on previous answers. Okay, let's say for this question number 8, let's just look at this one. Let's see. It tells us an athlete swings a ball, so we assume it's going to be uniform circular motion problem. So an athlete swings a ball connected to the end of a chain. So let's see, this is the athlete at the center. Look, I can only draw stick figures. The best I can do. Let's draw the stick figure closer to. So here we have stick figure. Let's call him Sticks. Okay, so Sticks has this chain. Okay, here's this chain. And connected to the end of this chain is this big ball. Okay, this big ball. And he begins to swing it horizontally, okay, in a horizontal circle. Okay? Meaning, if you were to look at the top of Styx's head, this would be Styx's head, this would be the chain from his hands, and this would be the big ball. This is the ball. And Styx is swinging this ball in a circle. Okay? He's swinging it in a circle around himself. Now, they tell us that this athlete, we've called him Styx, is able to rotate the ball at a rate of 8 revolutions per second. Okay, so now they are giving us information. Always write down information that's been given, whether relevant or not. So you will see then, I've often found that if I write all the information out and whatever I need, write it as well there and just a question mark next to it. For instance, they've given us the rate of revolutions per second is 8. So the number of revolutions per second is 8. Revolutions Let me just write it here. We'll get to that in a moment. 8 revolutions, 8 revs per second. The rate of rotation is 8 revolutions per second. This is angular speed, I think. Let me just get back to the actual notation. But the length of the chain, let's say LC, length of the chain is, let me just scroll up, is 0.6 meters. When he increases the length of the chain, okay, let's just call this initial length. Length initially is equal to 0.6 meters. But then he increases the length, so length, let's call it length final, is 0.9 meters. He's able to rotate the ball only 6 revolutions per second. So this is a rate of rotation. Let's just call it rate of rotation. And finally, I think I should actually write it here. It's 8 revolutions. Yeah, 8 revs per second. Same thing as when you accelerate your car. Now the next one would be 6 revolutions per second. If he increases the length of the chain. Think about that for a moment. Okay, you are swinging a tennis ball attached to a piece of string. Okay, you begin to swing it around. Okay, if the string is short, the amount of revolutions in 1 second is 8. Okay, but if you increase the length of the string, it now has to travel a longer distance, or a circumference of the circle is much longer now, so it will take less revolutions per second. Does that make sense? Okay, for those of you guys who are still listening, does that make sense? Okay, if you were to increase, let's say you attach a tennis ball to a piece of string, you begin to swing it around. Okay, if you increase the length of the string, it takes longer for the ball to go 1 revolution or once around you, meaning it will take much less revolutions in a second. Okay, now let's start. Question number 1. See, you must always read and understand and ask yourself if what is being said makes sense. Okay, in this case it makes sense what has just been told to us. Okay, so which rate of rotation gives the greatest speed? Okay, how do we get the speed from rate of rotation? Okay, speed, we have that speed is equal to, can anyone tell me what is speed? Let me just go back to first principles. What is speed? Speed is equal to distance divided by time. That's speed. Speed is distance by time. Okay, okay, I see. Yes, okay. Miss Hiles, thank you. Speed is the rate of change in distance over time. So speed is distance over time. Now what's the distance that you travel in a circular path? Okay, what's the distance that you travel in a circular path? It would just be, let's say this is a circular path. How would you calculate how much distance you've traveled in that circular path? it would of course be the circumference of that circle. And Yanela, I assume that's what you were about to say. Let me just wait until you finish typing. Alizwa. Yes, 2 pi what? There's something missing. Alizwa, you forgot. Yeah, Yanela got it right. 2 pi r. That's the distance you travel in a circle, okay? Divided by the time it takes you. That would be your speed, okay? If you're traveling in a circle. Now, let's do some quick converting, okay? 8 revolutions. This is why I originally did not want to write it down in give it a connotation, because we are going to have to convert anyway. 8 revolutions per second and 6 revolutions per second. We're going to convert them now. 6 revs per second. By the way, this is the same revs that you get in your car. Now we know that time is equal to the inverse of revolutions per second. Okay, inverse of revs per second. So this is 8 revs per second. 1 revolution divided by 8 revs per second will give you your answer in units of time. 0.125 seconds. Okay, your answer is in seconds. So the time it takes for 6 revolutions is equal to 1 over 6 revs per second. By the way, this is 1 revolution over 8 revolutions per second, and 1 revolution over 6 revolutions. You don't have to write the revolutions part. You can just write 1 over your revolutions per second, and it will give you your answer in units of time. Whatever your units of time, it could be revolutions per minute, and your answer would be in minutes. In this case, it's in revolutions per second, so your answer for time would be in seconds, and it would be 0.1,667 seconds. Okay, and that's 0.125 seconds. Okay, let me just write it neater. Time is equal to 1 over revolutions per second. Okay, and it will give you your answer in seconds, and we just did that. Okay, we just did that, and we've worked out that the time for to complete 8 revolutions in a second. Now note, we earlier on we said that it takes longer to traverse a bigger circle, so the bigger the radius, the longer it takes. Let's see. And we can see that for the one with the radius of 0.6 meters, for the radius of 0.6 meters, the time is equal to 0.125 seconds, and we've just worked that out. But for the one with the radius of, what's the other radius, 0.9 meters, the time it takes to complete one revolution or once around it is 0.167 seconds, and that makes sense. Okay, because it's traveling a longer distance due to the radius being longer. It's traveling a longer distance, which means it will take a bit longer to complete one full circle. Okay, so now we have times. Okay, how do we get this? As a side note, we will need that later on. Now back to what we want. Okay, which rate of rotation, meaning they want a speed. Okay, at what speed? And we've already determined it's 2 pi r, which is the distance divided by the time. Okay, so for the first one, okay, for the one that is 6 meters, 0.6 meters, the speed is equal to 2 times pi times 0.6 meters, and then the time it takes is 0.125 seconds. Your answer will be in meters per second, and if you were to work it out, I have confidence that all of you can just punch that in a calculator. You have 30.2 meters per second as the answer. That's how fast the first ball is moving. Let's look at the second one at 0.9 meters. The exact same calculation, 2 pi r over the time. We know that 2 pi is constant. The radius is now 0.9. It's longer. And the time is 0.167 seconds. That's meters. So your answer now is 33.9 meters per second. So the longer the radius, in this case the longer radius, 0.9 meters, is traveling faster. Okay. So we have each one's speed. Okay. 30.2 and 33.9. So we have the speeds, we have the time. That is question number 1. We worked out the time, which gives us the ability to calculate the speed for each ball. Now, let's say, what's the centripetal acceleration? So, AC. We calculate centripetal acceleration using v squared over r. Okay. We've already worked out for the 0.6 one. We have that for the 0.6 meters radius ball, we have that the speed is equal to 30.2 meters per second. We square that. We have that the radius is 0.6 meters. And that gives us an answer, or should give you an answer of 1.52 times 10 to the 3 meters per second squared. Meters per second squared. So this thing is moving very fast. Okay, it's 1520 meters per second squared accelerating. Now the triple acceleration for the one that has a radius of 0.9 meters, we said that its acceleration, or we calculated its acceleration to be 33.9 meters per second. We square that. Its radius is 0.9. That gives us an answer of 1.28 times 10 to the 3 meters per second squared. So we've worked out the centripetal acceleration for both cases. Now, last one. Number 3. They ask us, what's the centripetal acceleration at 6 revolution? We've worked out both of them. Okay? So the one was number 2 and the other one was number 3. We've worked out the centripetal acceleration for both. And here we have the answers as we've worked it out. You can just freeze the screen there if you don't understand. Just raise your hand. Otherwise, I will go to the next one. Question number 9. If there are any questions, please just raise your hand so I can answer them. Simple circular motion. We have number 9, a car tire. It has a radius, so this is the car tire. This is the radius. It has a radius of, car tire has a radius of 0.5 meters, so half a meter radius. And it rotates at a constant rate of 200 revolutions per minute. So it's 200 revolutions per minute. So we can work out the time. Let's work out the time. T is equal to 1/200 revolutions per minute. So there's 200 revolutions per minute, which means our answer will be in minutes. But we don't want the answer in minutes, so how do we get rid of minutes? We multiply by 1/60. Seconds. Okay, because that's 200 revolutions per minute. You flip it over, it becomes 1/200 minutes per revolution. So this would be 60 seconds. Yes. 60 seconds here, and 60 seconds is equal to 1 minute. Convert. This should give you an answer. Or a time of 10.5 meters per, no, sorry. We just check correctly my calculations. 10.5, which is 60 divided by 200, that one cancels. Seconds cancel out. No, we want seconds. Minutes cancel out. Revolutions cancel out because that's one revolution. That's cancels that one. That's 6 divided by 20. Let me just check on the calculator here. I did it all in one step, so let me just check here. Calculator, so I can show you guys as well. That is 60 divided by 200. That's 0.3. So 0.3 seconds. So 0.3 seconds. Okay, that's what we've been given. 0.3 seconds is the time. Now they ask us in this question, find the speed and acceleration of a small stone lodged in the thread of the tire on its outer edge. Okay, so speed would be the speed of the stone. Let's call it speed of stone is equal to 2 pi r. We've used this formula before. It's the circumference of the tire, because that's the distance the stone is going to travel, divided by, we just check if there are no questions yet. None so far. Divided by the time taken. In this case, it's 2 pi times 0.5, which is the radius of the tire, over the time of 0.3 seconds. And that gives you a speed of 10.5 meters per second. That's the speed of the stone. Now, what's the angular acceleration, or the centripetal acceleration of this stone, rather? That is the speed squared divided by its radius. Now, the speed squared, we've already worked out the speed is 10.5 squared over the radius of 0.5. That gives us an answer of 219 meters per second. That's 219 meters per second. Okay? 219 meters per second. That's how fast. That's the acceleration of a stone lodged in this tire. Have you noticed that these accelerations are quite high? Okay, circular acceleration are quite high because it's squared of the original speed, directly proportional to the square of the speed of the car, inversely proportional to the tire, meaning the smaller your wheels, the higher your acceleration will be. The tire's acceleration, which in turn would be the acceleration of your car. Okay, you can now actually prove that. Okay, now question number 10, last one. Okay. This is now where motion in one dimension becomes relevant. Okay, we have we have a question saying an automobile manufacturer claims that its product will starting from a rest. Okay, so the initial speed is 0 meters per second. Okay, so it starts from rest. Okay, it'll travel a distance x of 0.4 kilometers, so that's 400 meters. Let's rather write it in meters. 400 meters in 9 seconds. Okay, 9 seconds. This is the claim that this car manufacturer made. Okay, this car manufacturer made this claim. What is the magnitude of the constant acceleration? So how fast must this car be accelerating to achieve this particular feat? Okay, now we know from our formulas that the change in speed, the change in distance from x final minus x initial, x final minus x initial, so the change in distance, so basically this is just the distance, this is this delta x, is equal to the initial speed times time plus a half times the acceleration times the time squared. Okay? Speed times time gives you units of distance. A half acceleration times time squared gives you still distance, which is what we want. Okay. If you have a question, just ask me, raise your hand or whatever if you're still not with me so far. Now we want the acceleration. Okay, we want the acceleration. If we rewrote this formula, and you can do this by yourself. Okay, let's see. Let's rather do it slowly. Let's take initial speed, this term over. So we have final minus x initial minus vi t, and we're left on this side with a half times acceleration times time squared. If we get rid of a half and t squared, so let's keep a half times the acceleration is equal to the final distance minus initial distance minus vit over the time squared. Now let's go fill this in. Okay, so we have a half times the acceleration is equal to the final distance minus initial minus vi times t over time squared. If we were to plug in everything here, this is still a half acceleration. We can take it over, but I'll rather just keep it there for now. We have that final distance is 400 meters. It started from rest, which is 0 meters. We write in meters there. Minus its initial speed was also 0 meters per second. And the time is 9 seconds. And that's 9 seconds squared. So the answers on there on top would all be in meters. Whatever you get on top would be meters, and on the bottom it would be seconds squared. Okay, if you work this out, 400 minus 0 is still 400, minus 0 is 400. 400 divided by 9 is followed by 9 seconds. So it is 400 divided by 9. Let's see. Clear? 44.4. So we have that it's 44.44 meters per second squared. But please note, oh, I did not square, sorry. I forgot to square here. There's the problem. Should be divided by 89. 9 squared is 81, correct? Should be 81 seconds squared. So it should be 400 divided by 81. They'll give you 4.9. 4.9, which is what I have here as well. 4.9 meters per second squared. But remember, this is half of the acceleration. So this is half of the acceleration. So to get the full acceleration, therefore, we multiply both sides by 2. We get that 4.9 times 2 is 9,9 meters per second squared. You could have multiplied back at the beginning, but I chose to do it here. Okay. Now, ladies and gentlemen, that is all. Okay, there is some simple problems based on motion in one dimension. We did a few circular motion problems and motion in a plane. Okay, are there any questions? If there are no questions, then I will see you next week. All the best, and thank you for listening and participating, those of you who participated. Yanela, thank you. You reminded me that it's squared. Thank you for that. Thank you guys. Enjoy the rest of your day and all the best.